In this video, we will analyze the effect of the thermal noise in a coherent receiver. In particular, we'll consider that we have thermal noise at the input of a coherent receiver with the usual statistical model for thermal noise. It's an stationary, anergodic, wide and Gaussian random process with power spectral density n0 halves. Then we have a noise filter that is fitted to the characteristics of the modulation. Then a product with the cosine and a low-pass filter with the bandwidth equal to the bandwidth of the modulating signal, B hertz or W 2 times pi times B W radians per second. Now we will analyze the power spectral density of the filtered noise NF. At the output of the filter, the power spectral density is the power spectral density at the input, n0 halves, times square modulus of the frequency response of the noise filter. Then we have the product with the cosine, and we will analyze the power spectral density of the noise term xn of t. In this case, the product with the cosine in the time domain will produce two shifted replicas of the power spectral density of NF shifted to plus and minus omega c, and each one with 1/4 of the previous amplitude. If now we replace the expression for SNF here, basically we have N0 divided by 8 times two replicas of the square modulus of the frequency response of the noise filter shifted to plus and minus omega c. Now we have the low pass filter, and taking into account that the bandwidth of the signal, the low pass filter is only limiting this expression here to the range between minus and plus the bandwidth. It's very simple to check this. Finally, this is the expression for the power spectral density of the noise that we have here at the output of a coherent receiver. Now we can compute the power of this term just by integrating the power spectral density. We are integrating this expression. The integral is just between minus and plus the bandwidth in radians per second, and if we replace now this expression here, we obtain this final result. We have n0 divided by 8, and then we have the addition of two integrals. The integrals of the shifted versions of the square modulus of the frequency response of the noise filter between minus and plus the bandwidth. Now we are going to analyze the two integrals that we had in the previous expression multiplying to n0 divided by 8. With a very simple change of variables, it's possible to write these integrals in terms of the integrals of a square modulus of the frequency response of the noise filter between omega c or minus omega c minus and plus the bandwidth. Taking into account the symmetry of the frequency response of the modulus of the frequency response of the noise filter, is straightforward to see that this integral is equal to this integral, and we can write the addition of the two integrals as 2 times the integral between omega c minus and omega c plus the bandwidth of a square modulus of the frequency response of the noise filter. Therefore, the power of the noise at the output of the coherent receiver is equal to the product of this integral with 1/4 of n0. Now we are going to compute this integral for the filters that are used for the different amplitude modulations. And with this integral, we'll obtain the noise power at the output of the coherent receiver for every modulation. We will consider ideal filters to have the best possible behavior. The ideal noise filter for a conventional AM and for a double sideband modulation is the same one, because the spectrum of these two modulations have a support between the carrier frequency minus and the carrier frequency plus the bandwidth of the modulating signal. It is easy to obtain the integral of this filter in this range because we are integrating 1 in an interval of length 2 times W. This is 2 times W divided by 2 times pi is equal to 2 times the bandwidth in hertz of the modulating signal. Basically, the integral of this ideal response is equal to the bandwidth that we have in this range, that is 2 times B in hertz. Therefore, the noise power at the output of a coherent receiver for these modulations is this integral times 1/4 of n0, which is equal to 1/2 of the product between n0 and the bandwidth in hertz of the modulating signal. For a single sideband modulation, the ideal noise filter is an ideal filter between omega c and omega c plus the bandwidth for the upper sideband option, and equivalent between omega c and omega c minus W for the lower sideband option, but the result is going to be the same one. Now the integral of this response in this interval is equal to the integral in this interval, and it's straightforward to see that we integrate 1 in an interval of length W. This is equal to W that divided by 2 times pi is equal to the bandwidth in hertz that we have in this band over here. And this means that the noise at the output of a coherent receiver for a single sideband modulation will be 1/4 of n0 times the bandwidth in hertz of the modulating signal. And finally, for the vestigial sideband modulation, in this case again for the upper sideband variant, now the ideal noise filter is an ideal filter that has a bandwidth, the bandwidth of the modulating signal plus the vestige in of the modulation, and it's straightforward to see that the integral of this response in the range between omega c minus W and omega c plus W corresponds to integrate a constant value 1 in an interval of length W plus the vestige that in hertz, we have the result divided by 2 times pi is B plus delta B. The bandwidth in hertz of this, the bandwidth in hertz of a vestigial sideband modulation. And this means that the noise power at the output of a coherent receiver for this vestigial sideband modulation is just 1/4 of the product of n0 with the bandwidth of a vestigial sideband modulation, the bandwidth in hertz of the modulating signal and the bandwidth in hertz of the vestige.